All right, everybody, let's get started. A couple of reminders really quickly. Make sure that you make up the bond identification lab if you haven't done it already. I think there's only like maybe 2 or 3 people left that have to do that, so don't know who they are, but if it's you, get in there and do it. We want to put stuff away before break gets going so that we have not have to worry about chemicals kind of sitting out open or in a place we don't want them to be over an extended period of time. So make sure you do that. Also, if you haven't done this already, the molecular geometry quiz, do that as soon as you can too. Hopefully get that done. It's pretty fast. It doesn't take terribly long to do. It seems like a lot of people were able to get it done almost in what odds of home time. Nomenclature 1 is due tomorrow. So hopefully you've been working on it a little bit at a time. You didn't have to try to like power through the whole entire worksheet. In fact, it's probably a little bit better that you do it a little bit at a time, so you kind of take a break, let your mind digest it a little bit. All right, then what we're going to do today, we are going to, first of all, review those molecular compound or ionic nomenclature from worksheet number 1 here, nomenclature 1. If you have any questions. Then what we're going to do is we're going to talk about how to write chemical formulas using polyatomic ions. This is all about polyatomic ions today. So writing the formulas for them, and then also the flip side of that is coming up with their names. So writing the formula from the name and getting the name from the formula. That's our goal for today. All right, so are there any questions about worksheet number 1 there, nomenclature number 1? Anything you want to go over, any questions that you have? Any examples you would like to see done? Everybody's good to go. All right. Just like last week. All right, so on your worksheet, you need to write down a couple of things here. First of all, what does polyatomic mean? Poly means many, several. And of course, atomic just means atoms. So we're talking about having many atoms present. And we attach that word ion at the end, so we're going to have a charge. So these are groups of atoms, at least 2 at the minimum, some as many as like 6 or 7, maybe even more. There are a lot of polyatomic ions in there. But there's a bunch of atoms that have grouped together, they've bonded together. We've drawn them already with Lewis structures. We've already seen their 3D structure. Now we're going to be working with them, trying to see how do they come together to make compounds. So, not too different than what we've already talked about. Same deal because we're talking about ions. So it's just like ionic compounds where you just have a metal and a non-metal element combining. It's a cation combining with an anion. Cation goes first, anion comes after second. Still the same. Key thing for being able to work with these is identifying which one you're working with. Are you working with an element off of the periodic table that's become an ion, or are you talking about a polyatomic ion where you got several different atoms grouped together with a charge? The key for that is that suffix ending. Suffix ending. Sodium sulfide has that "ide" ending. That's usually a tip to us like, oh, ide, that's an element on the periodic table. So I got to change that "ide" back to what it was before. So sulfide, that's got to be sulfur. So I go and I look that up on the periodic table, get its charge. For sulfur, when it becomes sulfide, it's a 2- charge. So when I go to write this formula, I know I've got sodium from the name. That's the cation. And sulfur is giving me my anion. So I put those 2 together, do my crisscross. I need 2 sodium, 1 sulfide to make this compound happen. Na2S is my formula. That should be reviewed. But what if we had something that looks almost the same, sodium sulfate? It's that ending again. You need to be able to recognize that. That 8 suffix at the end tells us it's a polyatomic ion. Whenever you see an 8 or an ite, guaranteed you've got a polyatomic ion present. That's part of your anion. So this is something we're going to have to look up. So on the back of your note sheet, you've got a list of the polyatomic ions we're giving you. And on that list, you've got little stars by some that you need to memorize. You need to memorize not only their name, but also their formula, and along with the formula, their charge that they would have. So you need to have all of those things memorized. I'm only giving you a few to memorize, not too many. The other little small strip, the small sheet, has the polyatomic ions that we're not requesting you to memorize. So you have that kind of like a little handy little sheet. So after you got the other ones memorized, you can use that one for the ones that you don't have to memorize. So in this case, we've got sodium sulfate. We know that sulfate, you look it up or have it memorized. You go, oh, SO4 with a 2- charge. I'm going to combine it just like I did sodium sulfide. I do have to do my crisscross. And it causes me to realize that I need 2 sodiums, bless you, 2 sodiums and 1 sulfate. Because my 2 sodiums will give me a +2 total to balance out my -2 that comes with the entire package of an SO4. So Na2SO4 is my formula. Any questions on that? So still the same rules. My cation goes first, my anion goes last. That hasn't changed. The only thing that's going to be a little bit tricky is when we deal with polyatomic ions, we need more than one of them. So here's the list of polyatomic ions. This one has the ones on here that you need to memorize. So how many of them is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's not bad. So another example. You should be able to recognize the names for these 2 different compounds. Aluminum nitride and aluminum nitrite. Very close. In fact, it's only 1 letter different. But when you see nitride, that should automatically tip off your mind, like, oh, it's an I, it's an element most likely on the periodic table. There's going to be a couple of exceptions to that. So we know that's got to be nitrogen. Go look, oh yeah, it's in group 15. It's going to be a 3- charge. Aluminum is a metal. We know that's on the periodic table. Find that in group 13, so we know that's going to be a 3+ charge. So we've got aluminum with a 3+, nitride with a 3-. Don't use the crisscross unless you know you need to reduce that down. You don't want to get Al3N3. We just need 1 of each ion. We just need 1 aluminum ion and 1 nitride ion with a +3, -3 to combine and make our formula ALN. On the other side, though, nitrite, we're going to have a polyatomic ion present. We see that ite, that should tip you off right away, polyatomic ion, guaranteed. Go look it up or have it memorized. This one should be memorized. Nitrite. NO2 with a negative charge. So when I combine this one together, I've got Al with a 3+, and I've got the nitrite with a -. So when I go to make my crisscross here, it looks like I would end up with Al and then NO2, and then I put the 3 here. That doesn't quite look right. I don't think that's what's going to be happening. We're not going to end up with 23 oxygens. Because that's what that's telling me. I've got 1 aluminum, 1 nitrogen, and 23 oxygens. Oh, time out. We got aluminum, which has a +3. And I'm going to be combining it with nitrites, which have -1 charges. I know I need to have 3 of them total. Because 3 nitrites gives me a total negative charge of -3. To cancel out the +3 coming from just the 1 aluminum ion. So it'd be tempting to write Al and then N3O6, because that's kind of what we have. We have 3 nitrogens here. We also have 6 oxygens. That doesn't quite look right either. Is this like aluminum's in the center? We've got like 3 nitrogens and 6 oxygens somehow bonded to it? No, that's not the case. The NO2, a polyatomic ion, is kind of a package deal. Right? It's going to be combining as a group. So it'd be great if we could write out the formula to kind of represent that those atoms, that 1 nitrogen and 2 oxygens are together as a group. So the way we do that it's really tricky, is we use parentheses. That's a parentheses. We put parentheses around the formula for our polyatomic ion, because we know that those are together as a group. And then we put the number that we need of them to make this compound happen after the parentheses. So it's still kind of following that same rules for writing out our formula. So that 3 is really kind of distributed into those parentheses. So we have 3 nitrogens here, and we have 6 oxygens represented. But we've done it in a way that we can now look at that and identify, oh yeah, there's NO2 there, that formula, I know that formula. NO2 is nitrite. We have that one down. Any questions about that? So, you might want to write that down somewhere. If we have to represent 2 or more polyatomic ions in a formula, we have to put that polyatomic ion formula in parentheses. Gotta have those parentheses. So it'd be really tempting to put parentheses around everything all the time. Except it's kind of against the rule. If you have 1 polyatomic ion that you need, if I just needed 1 NO2, I don't put parentheses around. Put parentheses around it, it's going to be like, whoa, is there supposed to be a number that comes after it? That's normally what that would mean. So just 1 polyatomic ion, no parentheses, but if you have to have 2, 3, 4, however many, you need parentheses around it. All right, so let's take a look at a couple more examples. This guy, ammonium dichromate. Is there a polyatomic ion in there? Yeah, definitely. I see an 8. That's usually a good indication that I've got a polyatomic ion, having that 8 present. But what about ammonium? What element is that? Sounds like it's an element. It's not like sodium and potassium, calcium, barium, the ium thing at the end. But I don't see no ammonium on the periodic table. Can't find it on the periodic table. Where is it going to probably be found? A polyatomic ion. Look down at the right-hand column down towards the bottom. It's the 1 positively charged polyatomic ion you need to memorize. Because it breaks my heart every time when I'm giving out a test on polyatomic ions or naming systems and somebody comes up and says, I can't find ammonium on the periodic table. I say, it's not on the periodic table. It's polyatomic ion. So it's NH4 with a positive charge. So you have that one memorized, you see ammonium, you automatically know NH4 with a plus, and we're good to go. Dichromate, I know that's a polyatomic ion because it's got the 8 ending, so I look up its formula and charge, Cr2O7. And its charge is 2 minus. So I'm going to put these 2 together. I'm going to cross my charges. Ammonium's got a plus. Dichromate's got that 2 minus. It tells me how many ammonium am I going to need. 2. I need 2 of them. And it's a polyatomic ion, so what does that mean? If I need 2 or more of a polyatomic ion, I need parentheses. And then I'll only need 1 dichromate. So I put my parentheses around my ammonium because I need 2. No parentheses around that dichromate because I've only needed 1. Write NH4 2 with parentheses, Cr2O7. Any questions about that one? That was pretty easy. Go a little quicker to get this down. Next one, magnesium hydroxide. Well, magnesium, I know, well, that's not ammonium, so I know it's not a polyatomic ion. So magnesium would be on the periodic table. So we go look up magnesium. It's got a 2+ charge because it's in group 2. But what about that hydroxide thing? We're looking at the name, and I see an I that usually means it's on the periodic table. Yeah, it's a monatomic ion. It's a non-metal somewhere in the upper right-hand corner. The only problem is there's no changing this back to a name that would be an element. There's no hydroxygen or hydroxine or hydroxyphosphor or anything like that. There's nothing like that's going to happen. This is a polyatomic ion. There's a few of them that we have that have an "ide" ending. So they're a little tricky. But the nice thing is that they have the "ide" for the nonmetals. There's not very many nonmetals. So if you go through the periodic table and you don't find anything that looks like the name of it, you're probably going to have to go to take a look at your chart for your polyatomic ions, and it'll be on there. You know, if it was a metal, we'd be frustrated because there's a lot of metals in there. So hydroxide is our polyatomic ion. It's OH with a minus charge. These are the three that we have that have "ide" endings. They're a little tricky. Hydroxide, cyanide, and peroxide. So don't go looking for those guys on the periodic table. You'll be in trouble. So we go ahead and make this compound happen, make the formula. It's still the same rules. My cation and my anion. So Mg with the 2+, with an OH with a minus. I need 2 OHs. Cross my charges. 2 goes with the OH, only a 1 with magnesium. Don't forget your parentheses. Hydroxide's a common one people forget the parentheses with. Because a lot of our polyatomic ions end with oxygens, like O3 or O4 or something like that. So a lot of people are you're used to seeing like something with O and I need more numbers. Yeah, I put the parentheses and I put my number. For some reason, OH, people forget to put the parentheses on. So don't forget. Any questions on that one? All right, one more that we're going to get the formula for. Iron 3 carbonate. I see that 8 ending, I know I've got a polyatomic ion. I look at this guy, iron 3, what does that Roman numeral 3 tell me? It tells me the charge. It tells me that iron is going to be a 3+ charge. So that's always helpful. One of the nice things about those Roman numerals is that when we're writing out the formula, it helps us get the name. When we're going the other way, trying to get the name, they can be a little bit of a pain. But, all right. Carbonate, CO3 with a -2 charge. We're going to put those together. So you see carbonate, you know it's a polyatomic ion, you either have it memorized or it's on your chart. Write the formula down. There it is. We cross our charges. We need 2 iron 3 ions to make this compound happen. And we need 3 carbonate ions. So Fe2, CO3, 3. Fe2, CO3, 3. Any questions on how we got that one? Crossing the charges. 2, 3. It's really just kind of least common multiple. Figure it out. We need to get a 6. How do we get a 6 charge from iron? We need 2 of them. +3 and a +3 is +6. How do we get a -6 from carbonate? 3 of them. -2, -2, -2. All right. Now we're going to look at getting names from the chemical formulas. Yay. So here's an example of just our 2 elements combined together. Does this look like there's a polyatomic ion in it? No, definitely does not. It's binary. We just have 2 elements in there. Polyatomic compounds will have at least 3 different elements. So a metal and a non-metal. So this is just our regular ionic nomenclature we learned about just the other day, Monday. So we've got barium and then phosphorus. We have 2 different elements combined together. So if we're going to write the name for this, do I do anything to the name for barium? No, because it's going to be my cation. It's my metal, it's positively charged. We don't change the name for it. But phosphorus, my anion, what do we do to the name? Change it to ide. Yeah, I mean, ending to ide. So that's just barium phosphide. Binary compounds are pretty easy to do. Take your metal's name, and put your non-metal's name, and then just change it to ide. No prefixes on this one because it's ionic. Prefixes only go with molecular. So if this was a non-metal and another non-metal, then we'd have to put the mono, di, tri, tetra stuff in there. So the right-hand side of the periodic table, that's the key for being able to identify. Barium is way down in the lower left-hand corner. That's a big-time metal. So this is an ionic compound. Excellent question. We don't need to have that. We just talked about it. So here's an example. Ba3 and then PO4, 2. Does this look like it has a polyatomic ion in it? Yeah, there should be two big keys to saying, like, yeah, I know there's a polyatomic ion here. I've got 3 elements, barium, phosphorus, and oxygen. And I've got those parentheses in there. Ooh, we only put parentheses in a formula when we have a polyatomic ion. So, Ba is still barium. That hasn't changed. But now we need to be able to recognize that formula. PO4 is what? What is its name? Phosphate. So PO4 is phosphate, and then it's just the same as before. Just as easy for naming. Because before it was barium and phosphide, and you're done. It's the same deal here. My cation is barium ion, and my anion is phosphate ion. I just put the two words together and don't worry about the ion part. Barium phosphate. We're done. That's its name. These are easy. Barium phosphate. Take a look at the next one. This one's going to be a little bit trickier because I screwed up. I thought that PO3 would be on your list of polyatomic ions, and that's not. But we can figure this out. If you take a look at your polyatomic ion sheet, and we'll start in the left-hand column up near the top there, you've got chlorate and chlorite. What do you notice is different between the chlorate and the chlorite besides the names? Yeah, 8 has an extra oxygen, or one more oxygen than the ite. Easy way to remember that, 8. If you ate something, you've got a little bit more. You're bigger, fuller. So you got one more oxygen. You ate an extra oxygen. And you go down a little bit further, you find nitrate and nitrite, same deal. The nitrate has one more oxygen than the nitrite. So, I know phosphate is PO4, so what would this probably be named if it's PO3? Phosphite. So first of all, we got to look at the cation. We got nickel. Nickel's hanging out here. But nickel's one of those transition metals. Those ones can have more than one charge, unless it's silver, cadmium, or zinc. Or some other ones too, like yttrium. All right, so we know we got phosphite, so it's going to be PO3 with a 3- charge. And that's the key. That's the key for figuring out what charge your cation has. Both ways, both with just a binary compound, just a non-metal and a metal combined together, but also with polyatomic ions. Our anions only have one charge. So once we have that charge available, that can be the key to figuring out what the other charge is on our cation. So if I'm looking at this, I could kind of reverse crisscross and see, do I get the charge on my anion I'm looking for? That would mean there'd be a -3 here. Yeah, that is. So that means whatever this number is goes up here. That's going to be what my charge is going to be on that cation, that transition metal. So we do that reverse crisscross, get that charge. So this is telling me that nickel has to have a +2 charge. Must be that 2+. The only way it's going to work to get that to be neutral. So I have 2 phosphites, that's a total of -6. My nickel must be a +6 altogether, and there's 3 of them, so +6 divided by 3 is 2. It's 2. There it is. So I go to name this, it's going to be nickel 2-phosphite. I have to tell what ion is making it because nickel could have more than one charge when it makes a compound. This would be very different if it was nickel 3-phosphite. So it's still the same rules with those parentheses when you have a transition. Exact same rules. When they're writing out their name. Any questions on that one? All right, last ones to talk about. Oops, I didn't get rid of that one. So we got CuSO4 and Cu2SO4. So let's take a look at those. Copper is a transition metal, just like nickel. It can have more than one charge. So how do we figure it out? We use our anion. So we know this is combined with SO4. That's easily recognized. That's a polyatomic ion. One of the ones you should have memorized eventually, hopefully soon. SO4's got a 2- charge. Sulfate's got a 2-. All right, so if I'm looking at my 2 compounds then, if I've got CuSO4, I've got 1 copper combining with 1 sulfate. And I know my sulfate's bringing a -2 charge to the party. Copper has to be a 2+ then. It has to be. Because a 2+ and my 2- will cancel out, and that's what allows this compound to exist. 1 copper, 1 sulfate. 2+, 2-. So if I've got Cu2SO4, and I know that SO4's got a -2, coppers have to supply a +2 to balance that out. And since there's 2 coppers providing that +2 charge, 2 divided by 2 is 1, so it has to be copper with a 1+ charge. We needed those 2 copper +1s in order to get this compound Cu2SO4 to occur. So when I'm going to name these, I have to name them correctly. It is really tempting for people, let's say, to use essentially like the mono-di-tri system and go, oh, that's just 1 copper, so it must be copper 1. It has nothing to do with the number of atoms in the compound. It's the ion that makes the compound when it's an ionic compound. So this is copper 2 sulfate when it's CuSO4. It's made with the copper 2 ion. Copper +2. A lot of people will say this one's copper 2 sulfate, but that's wrong. You know it's not. It's actually copper 1 sulfate, because it was the copper 1 ion that made the compound. This is the toughest struggle I think most students go through trying to figure these things out. Is getting through that molecular naming with mono-di-tri, and then having this system, which is a little different, requires you to think a little bit more about what's going on with your compound. Any questions on this one? All right. So that, you don't have to write that down, but again, the Roman numerals are for charge, not the number of atoms in the compound. Only when you have 2 nonmetals are you going to have that situation. It's the only time. 2 nonmetals, you're going to be using the numbers in the compound to come up with the name. Mono, di, tri, tetra, penta, nona, octa, whatever. All right, so some tips for memorizing your polyatomic ions, because they're tough. It was one of the hardest things I had to go through was memorizing polyatomic ions. I now know a whole bunch of them. We don't expect you to know too many. Just memorize those big 11. But one thing there's 2 parts to memorizing your polyatomic ions. What charge does it have? And how many oxygens are going to be present? Because, like we saw, sulfate has got 4 oxygens, but nitrate has 3 oxygens. There's no consistency there. That's a little confusing. Some of them are a 1- charge, some of them are a 2- charge, and I got a couple that are a 3- charge. How do you remember? Well, one trick is if you memorize phosphate, which you should, PO4 is a 3- charge. Just have that one in your brain. Then all the other ones are either a 2- or a 1- charge. So we can use this an odd-even rule to figure this one out. So as an example, we got sulfur, or sulfate. Sulfate's SO4. So we got two different elements that are making that polyatomic ion. We got sulfur and we've got oxygen. So we go and we look on the periodic table, what groups are they in? Sulfur is in group 16, and 16 is an even number. Right above sulfur is the other element in this polyatomic ion, oxygen. They're in the same group. They're both in group 16. So if you added an even number with another even number, what do you end up with mathematically? An even number. And when you have an even number, when you're looking at the groups of the elements that make it up, you're going to have a 2- charge. Sulfate, SO4, is a 2- charge. Carbonate would be carbon's in group 14, which is even. Oxygen's in group 16, which is even. What charge would carbonate have? 2-. Even, you're going to have 2- charge. Let's take a look at the next one that's on here, chlorate. So ClO3, so I've got two elements here. I've got chlorine and oxygen. Well, chlorine is in group 17, which is odd. And we know oxygen is in group 16, which is even. Well, an odd and even together is odd. And your odds are going to be a 1- charge, -1. So where it says they're odd, you can put like your -2, or -1, sorry, and your even would be -2. So that's one way to kind of help you if you struggle with knowing what the charge is supposed to be. I'm really good at remembering SO4, and I can really remember PO4, but what is the charges in one of them? PO4, you should have that one memorized as 3 lines. The other ones, acetate. Ooh, that's a tough one. Acetate's got 3 elements in it. It's got carbon, oxygen, and hydrogen. Carbon and oxygen are both even, but hydrogen's in group 1, which is odd. So what's acetate's charge going to be? -1. Another example, cyanide. Cyanide's got carbon and nitrogen. So what's its charge going to be? Well, carbon's in group 14, that's even. Nitrogen's in group 15, which is odd. What's my charge going to be? -1, it's odd. Right, any other questions on that one? Another trick for memorizing your charges is memorize nitrate as -1, which you should. And then you look at these big 3 right here, which I think you need to memorize these anyway. But these ones all have a -3, -2, -1 charge. And we look at the elements that are not oxygen that are combined with them here, phosphorus, sulfur, and chlorine, they have the charges just like their monatomic, mono meaning 1, monatomic counterparts. So you look at phosphide is a -3, sulfide is a -2, chloride is a -1, just like phosphate is a -3, like phosphide. Sulfate is a -2, like sulfide. Chlorate is a -1, like chloride. Nitrate doesn't work because nitride's a -3, so it's an exception. Those darn exceptions, they're all so maybe that might help you. But here's the one that a lot of people struggle with. How many oxygens do we have? There's 2 things that we can help with that, so if you want to write these down, you certainly can. We already talked about this first part. 8 versus 8. We know that the 8 polyatomic ion will be 1 less oxygen than the 8. And the 8 is usually like our main number of oxygens, either 3 or 4. Like phosphate is O4. Nitrate is O3. Or 8s and their 8s typically have 3 oxygens or 4 oxygens. But the 8 one will always be 1 less than that. So nitrate is NO3, nitrite's NO2. There's a couple of other ones that will help us out, so make sure you get these ones written down. If you have a prefix on your polyatomic ion of per, followed by the 8 at the end, it's 1 more oxygen than the 8 has. Usually the 8 has 3 oxygens. So that our per 8 ends up with 4. And then the other one is when you have hypo as your prefix with ite. It's 1 less oxygen than ite even has. So it's like 2 less than the 8 would have. So here's our 2 examples that are on your polyatomic ion sheet. Perchlorate is ClO4, which means that's 1 more oxygen than the 8 would be, which is chlorate, which is ClO3. So if my 8 is ClO3, my ite has to be 1 less oxygen, ClO2. And then there's hypochlorite, which is even 1 less oxygen than that, ClO. Glad we're doing this lecture today because I got to remember, it reminded me that I have to do laundry when I get home. Sodium hypochlorite is the active ingredient in bleach. Talk about the chlorine and bleach, there it is. Hypochlorite. And I actually do need to do whites, so I need to remember bleach. Any questions on that one? So if you ever see per and an 8 together, you know, oh, I actually know what the 8 is. Like chlorate, I know chlorate's ClO3, so perchlorate must be ClO4. It's got 1 more oxygen. Anybody need this up for a little bit there? All right, then this one. This one involves some polyatomic ions that are not on your sheet, and that's okay. But this is kind of a helpful one when you're looking at the periodic table to try to figure out whether or not I've got 3 oxygens or 4 oxygens. And it only applies to the 8 versions of things. So phosphate and sulfate and nitrate and carbonate and chlorate, all those 8s. So the first one is the T part of the T41. Boron, carbon, nitrogen, and silicon. I know that's 4 atoms, but oh, we got almost that one. But if I connect these elements together, I get a T. So borate, carbonate, nitrate, silicate, they all have just 3 oxygens when they're in their 8 forms. So carbonate is CO3, nitrate is NO3, silicate is SiO3, borate is BO3. Borate you don't need to worry about, or silicate, unless you take earth science, then silicate is big. Next one. Phosphorus, sulfur, arsenic, selenium, and tellurium. That's 5 elements, but they equal to 4. Because if I draw those together, if I connect these ones together and then come over here and then go down, that makes a 4. So phosphate, sulfate, arsenate, they all have 4 oxygens with them. So it's PO4, SO4, 8SO4. And it would also be selenate and tellurate also. But we don't have those on your list, don't worry about it. And the last one is to make the 1, which we connect our halogens over here together. Chlorine, bromine, and iodine. They also have 3 oxygens. So the T and the 1 are 3s, the 4 is 4s. So chlorate is ClO3. Bromate would be BrO3. Iodate would be IO3. Any questions? Fantastic. We got a bunch of time then. I will hand out your assignment. We can talk about a couple of them. Go over a couple of examples. As you see, this worksheet's not due until Friday. And it's a little bit skinnier than the last one, which is good. So any of these you want to do as an example? Start with one. Potassium permanganate. Such a pretty purple color. So potassium permanganate. So we're looking at getting the correct formula from the name. So we're given the name. So we got potassium. Permanganate. That's a bad example because manganate's got two on it. We see the 8, we know it's a polyatomic ion, right? So we know we can go to our chart and look that one up. It's in alphabetical order, so go down to the bottom. Oh yeah, there it is. It's in the -1, down at the very bottom. Permanganate is Mn04, and it has a -1 charge. Potassium, that sounds like a periodic table element to me. So go find potassium. And it's in group 1. So it's a +1 charge. We have a -1 charge. Match made in heaven. KMN04. +1, -1. We're done. Love it when you have the same charges. +1 and -1. +2 and a -2. +3 and a -3. That's great. All right, let's jump down. Let's take a look at let's do copper 1 phosphate, number 17. We've got copper 1. Was it phosphate? So copper 1, that tells me automatically my cation charge. I've got copper with a plus charge. Phosphate, ooh, polyatomic ion, I see that 8. And that's one we should have memorized, PO4, with a 3- charge. Cross my charges to get my subscripts. I'm going to need 3 copper ions and just 1 phosphate. 1. Take a look at one where we might need some. Oh, perfect. Next one. Take a look at number 19 real quick. So number 19, we've got lead 4 nitrite. So I like the polyatomic, or the Roman numeral in parentheses. So I know lead is going to have a 4+ charge. Nitrite, I see that ite. I know it's a polyatomic ion. Look it up on my chart. NO2, a -1 charge. So I cross my charges. I'm going to need 1 lead. I'm going to need 4 NO2s. So I need my parentheses around my polyatomic ion. I need 4. All right, any questions on getting the formula from the name? All right, let's take a look at a couple of ones on the other side, the other column. Which ones do you want to do over there? Let's start off with number 2. Number 10? I'll take your word for it. It must be a tough one. Ca parentheses. That's a parentheses. Ca, C2H3, O2, and 2. Definitely know I got polyatomic ion here. There's 4 elements here. So it's always good to be able to start recognizing, being able to break things into 2 parts. In all of our compounds we're going to be working with, we got 2 parts. 2 parts to the name, 2 parts to the formulas. So here we have to have a cation and an anion. My anion's easy to recognize because it's a polyatomic ion in parentheses. So what's left must be my cation. So Ca is calcium. Is calcium a transition metal that we need to worry about Roman numerals and stuff? No. It's over in group 2, so it's one of the ones that don't have to worry about charge. It's only got a +2 charge. Then I just got to look up C2H3O2. Oh my goodness, it's the first one on the list. Acetate. That's it. When you're naming a compound, it's just those two parts. Your cation's name and your anion's name. Let's do number 20. Nice round numbers. So for number 20, we've got FeCr2O7. A little bit trickier to see the two parts here because I've got two metals here and then one non-metal. So I got iron and chromium and oxygen. But the first one is going to be my cation. The next metal, if I have another metal in there, it's most likely going to be part of a polyatomic ion. So I got Cr2O7, it's most likely a polyatomic ion. So Fe is iron. However, I do know iron is one of those transition metals. So we're going to need to worry about the charge it's going to have. Calcium, we didn't have to worry about it. It's always a +2. Iron, though, could be a +2 or +3. So it depends on what this guy is over here, Cr2O7. So I know that's polyatomic ion, I'll look it up. Dichromate. Dichromate. And this is why it's important to know not only the name and the formula, but to know the charge, because we need the charge to figure out what is my cation's charge. So Cr2O7 dichromate has a 2- charge. And I have no parentheses here, so that means there's only one of them present. I only have one dichromate package contributing to the charge that needs to be canceled out. So I got a 2- here. I only have one iron, so that means the iron must be +2. Because I have to have a +2 to cancel out my -2. So that would be iron 2 dichromate. Cool. Any other ones you have a question about? Any ones on the back or anything? Which one? 24. 24. Absolutely. 24 CaSO3. Since this worksheet's pretty much got all polyatomic ions, I'm pretty sure there's a polyatomic ion here. SO3, 2 nonmetals combined together. Yeah, that's got it. So I've got calcium combining with whatever SO3 is. I know Ca is calcium. I know calcium is a group 2, so I don't have to put the Roman numerals in parentheses. It's always a +2. I just need to figure out what SO3's name is. SO3 is sulfite. And we're done.
So that doesn't have any of the charge.
Does it have any of the charges on it? Yeah, this one doesn't have like the Roman numerals that we were asking. Yeah. Yeah, anything that's in group 1 or group 2 or group 13, you don't put parentheses and Roman numerals. And then the 3 exceptions that you should know from the transition metals are silver, cadmium, and zinc. They also do not need any parentheses with Roman numerals. They only have one charge. You don't need to put parentheses in here to try to distinguish what its charge is because it's only got that one. Any other questions? We got about 5 minutes. All right, well, the rest of the time is yours to work on the homework.